Hey Stats, so this is us going over the questions from 9.5. I'm just going to let you guys know I've had to clear my throat a whole bunch today, so hopefully I won't have to pause a whole bunch. But nonetheless, let's see if we can get through this without too much interruption. So the first question you were asked is, it says, you would expect that teams launching gummy bears would get better with practice. A bears in space data from chapter 4 is given below. It says you're going to test whether there's a statistically significant evidence that the teams improved from launch 1 to launch 10 using alpha equals 0.01. Now the first part of the question says, should you use a 2-sample test of the difference of the two means or a 1-sample test of the mean of the differences? Explain. Well, given the fact that you are having people launch these gummy bears, notice that it says first launch, 10th launch, I think we can safely assume that it's the same people or person launching the gummy bears each time. That means that you know that the 10th launch is certainly not independent of the first launch. There's going to be some skill here where people practicing basically causes, you would think, improvement. That's the biggest reason why you can't just use a 2-sample test. We're going to want to combine this data. State the hypotheses for your test. Our null hypothesis should be that the mean sub d, so mu sub d, with the bar above the d, is equal to 0. That would mean that the average difference is 0, or that there is no improvement whatsoever. The alternative hypothesis should be that mu sub d is greater than 0. Now, I said greater than, of course, because at the beginning of the question, it says you would expect that teams launching gummy bears would get better. Better means to improve by the 10th launch. And so if my difference is the 10th launch minus the first launch, then my mu sub d should be greater than 0. Remember, for your null hypothesis, you would want to state that your mu sub d represents the 10th launch minus the first launch. Does the result of the test seem sensible? What type of error might you have made? So it wants us to go ahead and do these computations. So before we can do any of that, though, we should check the conditions. So the conditions of this basically want this to be random treatments of some kind. Well, it's literally impossible for this to be random. You're comparing a first launch to a 10th launch. You can't randomly assign somebody to launch their 10th gummy bear first, because then it's not the 10th launch, it's its first launch. You can hopefully see that the randomness just doesn't happen. But that doesn't mean that this test fails. Randomness is done to eliminate a variable. We're actually not wanting to eliminate that variable. We're trying to specifically see if there is improvement here. So even though this might not necessarily carry over to a larger population of people, at least with these 6 teams, we can judge it to see if they have shown some sort of signs of improvement. If you'd like to see how the book kind of describes this, here's how they do. It says this is a repeated measure design. I'm in the top right column, by the way. You should use a 1-sample test of the mean of the differences. A one-sided test should be used because you want to test whether the teams improved. Beyond checking the conditions, it says this is not a random sample, and the paired observations are not in random order. This is an observational study of the teams. Now, they give us the box and whisker plot, which saves us a little bit of time, but I'd like to show you how you would check this on your own. So on the calculator, you can see that I've already plugged in all the data for us. But because we determined that they are not independent, we need to combine the data. So I'm going to highlight L3. I've actually plugged the 10th launch in for list 1 and the first launch in for list 2, just because to me that makes more sense. So now I'm going to take list 1 minus list 2. Now I have my differences, which not surprisingly are all positive. Now if I go to the plot, remember I don't care about the 2 launches separately. When combining data, I only care about what the box and whisker plot of the differences looks like. So I actually want to look at the box and whisker plot of L3. So I'm not going to be surprised by this because I just showed you guys the answer key. But if I do a zoom 9 on that, you can see the same box and whisker plot that is in my solutions. And yes, even though we have a very, very small sample size of 6, this one is actually pretty darn symmetrical, which means I think we're still okay to proceed, keeping in mind that this is only going to be representative of the 6 teams currently launching these gummy bears. So now let's go back to the calculator and run the calculations. Stat. Over to the test menu, and we will in fact be selecting just the t-test, not the 2-sample test. Even though we had 2 samples to start with, we combined the results into a single sample. The data is in my calculator, and the mu sub 0, the basically null hypothesis, is now our mu sub d. So the mean of the average of the differences. Okay, and we want that to be 0, because if we say 0, that means that we believe that there was no basically improvement from launch 1 to launch 10. Keep in mind that the data I want to analyze is in L3, and the alternative hypothesis on this one is definitely greater than, as we're trying to see if there's statistical evidence of improvement. Then when I calculate, I get a test statistic of 5.3 and a p-value of 0.0016. So that is a very small p-value even at the 1% level. That shows me that this result is statistically significant. I can reject the null hypothesis. I have evidence to support that among these 6 teams, there is pretty clear evidence to indicate that they have improved their launching distances from the 10th time they launched to the first time they launched. Okay? So basically, in this group of 6 teams, we have statistically significant evidence to show that by the time they've launched 10 of the gummy bears, their results have improved since the first time they had launched gummy bears. Part C said, did this result seem sensible? And of course, you practice something enough, you get better at it. What type of error might we have made? We decided to reject the null hypothesis. On the off chance that they should have not improved whatsoever, then we've technically rejected something that might have been true and therefore could have made a type 1 error. If you had used the other test, would the conditions have been satisfied? And of course the answer is clearly no. These were not independent samples. We already knew that there was a variable involved here that was going to cause these to be statistically significantly different, and that variable was repetition, practice. Them repeating the process over and over and over again meant that by the 10th time they did this, we expected there to be an increase. So there was no reason to run it as a 2-sample test, as it would be very meaningless. We knew there'd be improvement. The question is, was there statistically significant levels of improvement? And yes, we saw that there was. So the next question I asked you to do is very similar, but instead of looking at the quantity of times that they launched the gummy bears, we actually look at the number of books they used, which would have to do with the launch angle. Fun fact, I had the students try this one year, and 4 books, no matter what kind of book you use, ends up giving you a very, very vertical launch angle. So I don't know what kind of books they were talking about when they said 4 books, but 4 books was overkill. Every time I tried to practice this in class and do it, we ended up doing 1 book versus 2 books. And that ended up giving us a pretty significant difference in and of itself. So the 4 books versus 1 book is pretty interesting. Now this one says, should you use a 1-sample procedure or a 2-sample procedure? Well, here's the thing. Are we having the same group of people do it? Well, they did break them up into teams, so yes, it seems like we are having the same group of people do it. So that means that it isn't completely independent, because of course the one sample has got the same people in it as the other sample, and therefore, yeah, if one person or persons in the team is pretty good, they're likely to be pretty good regardless of how many books there are, and if somebody's really bad at it, they're likely to still be pretty bad at it. So these are definitely, once again, not independent. We really just are randomly assigning, hopefully, which one goes first with 4 books, which one goes first with 1 book, which they said they did by the flip of a coin. So we are going to once again use the one sample procedure by combining the data. Now to check the conditions this time, I will not be plugging them in on the calculator. I'm just going to show you the results here on the answer key. So if I scroll down here to number 71, you'll see that it told us we should use a one sample procedure for the mean of the differences because we have results of both treatments for each team. This is repeated measure again. Randomization means that the order of the treatments was randomly assigned, which check did work. The distribution has no outliers and no strong evidence of skewness. And even though some of you might be saying, well, isn't that pretty skewed to the left, Mr. Ryan? The arm is pretty skewed to the left, but if you actually look at the box itself is kind of skewed to the right. So this is one of the few times where looking at a box and whisker plot, unless you're familiar with this, those two things kind of balance each other out. So they are met. It's not the best, but it's definitely met enough. So we can proceed. So this time they do not want you to run a test. They want you to calculate a confidence interval. So you'll notice that down there it says with no rounding that you should get a 95% confidence interval of somewhere between negative 23.07 and positive 146.74. Now off the top of my head, yep, the units was inches. So this was the distance that the gummy bears were launched in inches. So that means that the difference between the 4-book launch and the 1-book launch is somewhere between negative 23 inches and positive 147 inches. So that really means that maybe launching with 4 books is causing you to not launch as well. And if you did use 4 books, you'd see that that might have to do with the fact that the angle being launched is just too steep. But most of the time it does appear that it has an improvement as much as 146 inches, which would be quite a bit. But nonetheless, 0 is in that confidence interval, so you do not have statistically significant evidence to show that one book's launch is better than the other. We definitely have just their different types of launches. Okay, it does want you to interpret that 95% confidence interval, so just make sure you talk about which order you subtract it in. I'm 95% confident that the difference between the distance launched with 4 books and the distance launched with 1 book is somewhere between the negative 23 and the positive 146 inches. So just getting the order right is what matters the most. For number 75, you can see that they went through a very rigorous process here where they talked about how they used the height of a step where 0 is for a 5 3/4 inch step and the 1s represent an 11 1/2 inch step. So hopefully none of you tried to plug in the numbers 0 or 1 in your lists. If you did that, you really made a mistake. Those are just representing the 2 types of steps. And they wanted to look at resting heart rate and exercise heart rate and see if there was a bigger increase, basically. So this one's kind of interesting in that basically what you want to do first is find out what the increase is. So you should probably take the exercise heart rate minus the resting heart rate for both groups. So the group on the left is the 1 step and the group on the right is the other step. So what you're kind of doing, is you're first doing the difference, the mean of the difference. But then rather than just see if that difference is statistically significant, you're comparing one type of step to another step. So this is kind of like doing the stuff we did in 9.5 twice, and then going all the way back to 9.4 and running one of the 2 sample tests. It's very interesting. So the first question says you want to test whether the higher step resulted in a larger mean gain in heart rate than did the lower step. Is this a 1 sample test or a 2 sample test? So this is actually a 2 sample test because you're going to be comparing the lower step to the larger step by getting the gains. So basically they just were very inconveniencing you by not telling you what the increase was. They could have literally just taken exercise heart rate minus resting heart rate and given you that value for the 0s and given you that value for the 1s, but they didn't. So they were really mean to you in that they just didn't give you the data you wanted right off the bat. Okay, check the conditions and then test whether the higher step resulted in a larger mean increase. So if I scroll down here, You guys can see it was a 2-sample test. First, subtract exercise minus resting to get gain. But then you're going to compare the gain for the 0 code to the gain for the 1 code. So you will have 2 treatments of size 15. So if you compare both treatments, you can see that the higher step, the 11.5-inch step, did have an outlier, but it's a very minor outlier. The rest of the data is pretty symmetrical. The lower step looks pretty good. So overall, you can proceed. Your null hypothesis should be, I guess if you wanted to get really technical, you could say like mu sub d sub 1, where you could say the mean of the differences of the people on a 5.7-inch step and the mean of the differences of the people on an 11.5-inch step. But you can still just call it mu sub mu sub 1 and mu sub 2. You'll notice that the answer key calls it mu sub 0 and mu sub 1. I hate that. I hate that so much. They assigned the 0 because the 1 was coded 0, and they assigned 1 because the 1 was coded 1. That seems messy to me. I would just assign mu sub 1 to the gain of the people on the 11.5-inch step and mu sub 2 to the gain for the people on the 5.75-inch step. That's the way I would do it, and I think that makes the most sense, okay? So if you took the gains, only the gains, you had to subtract the numbers first, plugged those into L1 and those into L2, and then compared L1 to L2. This would have been a 2-sample t-test on the calculator. You should have gotten a test statistic of 2.78 with a p-value of 0.0051. And obviously that is a very small p-value, resulting in a statistically significant result. Okay, so if we look at the top of the left column now, it says, this is strong evidence against the null hypothesis. You have statistically significant evidence that using the higher step increases heart rate more than using the lower step. So that is the full-blown way to analyze that. I have a feeling there might be quite a few questions from you guys on that one, but I will just tell you right off the bat that the quiz this week will likely not give you one like that. If I was going to give you a question like that, I wouldn't give you something where you had to subtract and then compare. I would have just given you the gains for each group, and then you would have compared the gains for each group. So it would have been a lot more straightforward. All right, the next question you had to do was number 79. And I'm looking at the answers before looking at the question. That's kind of silly. Let's come down. So hospital carpet. It says if you had to spend time in a hospital, you would want your room to have carpeting or bare tile floor. Carpeting would keep down the noise level, which would certainly make for the atmosphere to be more restful, but bare floors would be easier to keep free of germs. One way to measure the bacteria level in a room would be to pump air from the room over a growth medium, incubating the medium, and counting the number of colonies of bacteria per cubic foot of air. The method was in fact used to compare the bacteria levels in 16 rooms at a Montana hospital. 8 randomly chosen rooms had carpet installed. The floors in the other 8 rooms were left bare. The data is shown below. Which of the 2 designs, 2 independent samples, or paired data is the more appropriate model? Why? So this really honestly comes down to kind of a more, how did you interpret the way this was being done? I'll show you how the book describes this one. It says that for this one, this is a completely random design. The data is not paired. The 2-sample procedure is an appropriate way to compare them, as in section 9.4. Random assignment of treatments to subjects allows the same analysis as random sampling from 2 different populations. So what they're basically saying is you can compare the carpeted groups to the bare floor groups, and you should be good to go. Now, I think there's a lot of variables involved here. There has to do with location, different floors, different wings. Obviously, you're hoping that the floors, or sorry, not the floors, the rooms that they're comparing are actually on the same floor, in the same wing of the hospital, and have similar traffic, because of course traffic might have a lot to do with this too. So I think there's a lot of other variables to take into consideration, but in general, this would certainly be a simple 2-sample procedure. But, of course, the textbook then asks us for part B, which is just past Oh, they gave us the data. I was like, I got confused for the data. There we go. Tell us how to run the experiment using the other design. So I'll show you what the book said. The book says you might pair rooms, one with carpet and one without, that are near each other and have similar uses. This may be difficult, however, unless the experiment allows carpet installation long before the data are collected. Alternatively, you could use a repeated measure design giving each room both treatments. You need to randomly assign the 8 rooms to get carpet first. So occasionally I'll get students who will say, why not carpet half the room? And I understand in your mind you might be thinking, hey, then I get both treatments in the same room at the same time. I can just compare one side to the other. But there's no guarantee that one side is going to get used just as frequently as the other. Plus, the aesthetics of that probably mean that it's not likely to happen. I don't think most people would want their rooms to look that way in the hospital. So I get where you're coming from, and that doesn't sound like a terrible idea. It's just probably not very practical in the sense of things. I, of course, like the repeated measure. I think that makes the most sense so that you know that the rooms that are pretty much being tested are going to have equal-ish treatment overall. But yeah, I think they brought up most of the factors that I would have been worried about by saying that you'd want to make sure they're near each other with similar uses, etc., etc. So those are the kind of things to take in mind if you're going to start pairing them, or especially if you would want to repeated measure. Obviously, you'd have to be very careful on a repeated measure to make sure that any of them that had one over the other got like a full-blown cleaning before you would, repeat the process, because you wouldn't want any of the data from the one to bleed into the other. So a lot of different things to take into consideration, but it's a neat question to ponder. The final question I had you look at was number 85, Old Faithful. It says, the Old Faithful geyser in Yellowstone National Park got its name from the predictability of its eruptions, which used to occur about every 66 minutes. It says, for decades, visitors throughout the warm months of the year have crowded the large circle of benches surrounding the geyser as each eruption time approaches, waiting to see a 150-foot high, blah, 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 blah. In recent years, however, scientists have noticed that the times between eruptions have become somewhat more variable, and the distribution of times, in fact, appears to be bimodal, as seen on the next page we'll look at. Additional studies suggest that the time until the next eruption might depend on its previous eruption. To test this hypothesis, a science class decides to classify eruptions as either long or short, and then compare the mean times until the next eruption. So you can definitely see this bimodalness. All right, you have the interruption times, and you can see that there's kind of a peak around 78-ish minutes, maybe 80-ish minutes, and there's another peak near the 54-ish minute mark. It says, would this be a meaningful comparison? Why or why not? And I guess if your data is to try to see if there's some sort of predictability to it, why not? If you're going to separate them into two groups, shorter eruptions, long eruptions, as long as you have a definitive cutoff point and neither of those cutoff points are really overlapping, then that would be pretty good. You can see that the inner eruption time of 66 minutes seems to be almost non-existent. So I think you could classify long eruptions in that 72 plus category. I think that would be pretty good. Short eruptions in the less than 60 minute category, and you'd probably be okay. You just want to avoid getting to the overlap point, because then if you have a lot of things that fall into the overlap point, the comparison becomes less meaningful. So you just got to make sure that the cutoffs have some gap. It would have been great if this data had a definitive gap in it where just no eruptions occurred, then it would be really easy. They do appear to have a tiny bit of overlap, but I think the fact that like 63 to 66 minute range kind of collapse would allow you to get some good cutoff points there. And then it says, are the data on times between eruptions paired or unpaired? Well, obviously, these are random, if you will. There might be some sort of correlation between them, but they're most certainly random. So these are unpaired. But if you want to see how the book describes the answer, it says, comparing means would be appropriate if it's reasonable to assume that the students have a somewhat random or representative set of short and long eruption times. That's them knowing their boundaries. There's no obvious reason why this would not be the case. Note that the comparison to be made is between the length of time until the next eruption following a short eruption and the mean length of time until the next eruption following a long eruption. The difference turns out to be substantial, and then this is all just kind of fun fact stuff. After eruptions that last less than 3 minutes, the average waiting time is about 54 minutes, standard deviation of 6.3, and then for the long eruptions, the average waiting time is 78 with standard deviation of this. It says you can see the data, and they give us a footnote. The data can also be found at that website. And then, of course, it just simply says, with no explanation, that the interruption times are unpaired, which makes sense. So anyway, guys, if you were able to follow along, hopefully you realize that this section is kind of just building up more on the same. Getting the data typed into the calculator is the most important part. So if you did these questions before you're seeing this video, like you should, and you check your answers, and you now see the answers, and you're getting them right, then that just tells you that you're doing everything pretty good. Based on your guys' last quiz, the explanations are getting pretty solid. Remember, always in the context of the question. That answer quiz should have been emailed out to you. So make sure you take a look at the answers to see how you did on the previous quiz. So anyway, guys, this is going to wrap up Chapter 9 for us. You'll have a quiz over 9.5 later this week. Make sure you're looking for that. Get it turned in before Sunday, and I'll talk to you guys next week.